Okay, so in our first topic, or excuse me, our first unit looking at scientific literacy, for those of y'all who were absent from today's lesson, okay, um, we're looking at the difference between what's called the difference between science and what's called pseudoscience. Pseudo being meaning being a Latin word that means fake, essentially. Okay, so that's our topic for 1.1 scientific literacy: science versus pseudoscience. So what we're up to today, we'll learn how to distinguish scientific claims and arguments from non-scientific claims and arguments. What constitutes pseudoscience in this day and age? So we had a little warm-up discussion based off of Michael Jordan commercial. We'll move on from that. So here's a nice little discussion we also had based around trying to distinguish between fact and fiction. Is these following statements that we need to classify as true or false. The first one: the characteristics of the human skull can be used to determine mental ability and personality traits. The second one: as an object moves faster compared to its surroundings, time moves slower for that object. And then 3, vaccines cause autism and contain mercury, which can be poisonous for the human body. And then 4, homeopathy and water-based medicines are a suitable alternative for traditional drugs and medical treatments. So the point of this activity for students in the class is in order to demonstrate how we have a wide range of responses to each of these statements, and that it's very hard to classify each statement as true and false. Okay? In fact, the only correct statement out of these 4 is actually the second one, which might seem like the most science fiction-esque statement of all 4. So as an object moves faster compared to its surroundings, time moves slower for that object is a true statement on our reality. It is a consequence of what's known as Einstein's theory of special relativity. The other 3 statements all correspond to pseudoscientific beliefs or fictional scientific beliefs. Number 1 describes a fictitious scientific belief in the 1800s, or excuse me, better said, a false scientific belief in the 1800s known as phrenology. Number 3 is a belief that still persists today that we'll take a look at down the line and extensively throughout this unit, based on a falsified 1998 research paper by a medical doctor by the name of Dr. Andrew Wakefield. And then number 4, homeopathy and water-based medicines are a suitable alternative for traditional drugs and medical treatments. This is also an example of a scientific belief that is not correct. I don't want to say belief, but it technically is a belief because it's not technically science. It's what we call pseudoscience, which we'll define in a moment. So anyway, the point of this activity here is to illustrate how hard it is to distinguish between true scientific statements and statements that are not scientific in nature but are trying to pass for being scientific. So this brings us to distinguishments between what we call science and pseudoscience. So we know what science is. Science is the study of the world around us based off empirical facts and data and based off logic. Okay. Pseudoscience, on the other hand, consists of statements, beliefs, or concepts that may seem scientific in nature at first glance, but in reality lack scientific evidence and do not adhere to scientific method. Okay? Pseudo coming from, again, the Latin word for fake, so this means literally fake science. Okay? So an example of pseudoscience that still persists today is the flat earth movement, such as, well, the view espoused by Kyrie Irving that the earth is flat. Okay? So distinguishing between the two, how do we distinguish between fact and fiction? What is the real deal with real McCoy, and what is trying to pass itself off as actual science? Okay? So pseudoscience adheres to the following while science does not. Selective bias, aka cherry-picking evidence that supports their claim while ignoring evidence that does not. And you'll see this happen all the time, even in non-scientific arenas such as politics, mainly politics, now that I think about it, where people cherry-pick evidence to support their claims while ignoring evidence that does not. So an example with the anti-vaccination movement is, and with the flat earth movement as well, is that there's overwhelming evidence from the scientific community with the anti-vaccination people. There's overwhelming evidence from the medical community that there's no link between vaccines and autism. And then with the flat earth people, there are hundreds of years worth of evidence accrued by physicists that shows without a doubt that the earth is spherical in nature. It's actually more what's called a oblate spheroid, I believe, but that's another topic there. Anyway, people in both those camps, the anti-vaccination camp and the flat Earth camp, will ignore that evidence in favor of evidence that does support their beliefs. And oftentimes, this evidence tends to come from like celebrities. So you got like Jenny McCarthy, who says vaccines cause autism. Jenny McCarthy does not have a medical degree. You'll get people like Kyrie Irving who say the Earth is flat. And Kyrie Irving doesn't have a PhD in physics. Sorry to break it to you. All right. Pseudoscience avoids experimentally testing their claims. So every year, there is a big convention that gathers for flat earthers, okay? But they never, never, ever, ever, ever test out their claims. They come up with 100 billion different theories for what the Earth actually is, but they never actually test out their claims, okay? And in the rare once in a blue moon time that they do try to test out their claims, it always ends up contradicting them, okay? So lack of credible scientific sources. The sources cited to support a claim in pseudoscience are not scientific in nature. So again, people who think vaccines cause autism will look at sources that are not trustworthy sources. And if you're wondering how do we distinguish between trustworthy and non-trustworthy sources, that's when we'll look at that's what we'll look at down the line in this unit, specifically 1.2 and 1.3, lessons 1.2 and 1.3. Okay. Subjective validation. So pseudoscience will adhere to what's called subjective validation, meaning believing something to be true because it worked for you. So an example with that, example of that would be like if I had a headache and I ate some chocolate and my headache went away, and I said, there's a link between whatever's in chocolate and curing headaches. That would be an example of pseudoscience. My trying to pass that off as a scientific claim would be an example of pseudoscience. There may be a link, but we need to do extensive testing, experimental testing, in order to see if there is actually a link, which goes back to point 2 again. We avoid testing our claims if we have a pseudoscientific claim, okay? Making such a claim that chocolate cures headaches does not take into account maybe there's a bunch of other factors that were affecting the outcome, okay? So somebody could equally say, oh, it was raining that day, the rain cures your headache, okay? And again, that's where we need to do experimental testing where we have controls and we have independent variables and dependent variables in order to test out our hypothesis. In addition, we need to test our claim multiple times. We can't just test it once and say that it works. Again, in science, we need to do multiple times in order to make sure that our data is consistent and supports our hypothesis. Otherwise, it may have just been a pure coincidence that I ate chocolate and then by pure coincidence my headache also cured just at the same time, snap of the fingers. And there's no actual correlation. Again, correlation does not imply causation. And pseudoscience contradicts itself. So oftentimes, and this goes more into logic and argumentation, which we won't go too much into detail into, but people who espouse pseudoscientific beliefs tend to contradict themselves, okay? Meaning that their arguments fall flat on their face, and their arguments, if you dig in deep enough, will actually end up collapsing upon themselves. So with the flat earth people, they tend to have some very just crazy out there beliefs that if you dig hard enough will contradict themselves. And then again, in the rare case that they do try to experimentally test their claims, as we'll see on the next slide, it turns out their experimental evidence will contradict their claim. Now, this is not to say that any hypothesis that is wrong in science is pseudoscience. It's okay to be wrong in science. That's how we advance in terms of our understanding of the world. We make a hypothesis, we test it out, and either that hypothesis is correct or it's incorrect based on the data that we collect, okay? But pseudoscience would be choosing to ignore that data, choosing to ignore that evidence against selective bias, or avoiding to experimentally test our claim. Okay, science would be experimentally testing our claim, and if it comes back that the data supports our hypothesis, we accept the hypothesis. And if there's not data there to support our hypothesis, we have to discard our hypothesis instead of choosing to believe our hypothesis strictly because we want to believe it. So examples of pseudoscience. Again, trying to see right here, trying to say that correlation implies causation. Again, with all these conspiracy theories where people tend to link things that really aren't linked, or if they are linked, it's just pure coincidence. There's no causation. So that's again an example of subjective validation. I want to believe with the X-Files and UFOs. That's an example of selective bias. I want to believe something, ergo I'm going to ignore any evidence that does not support my belief, and I'm going to only cherry pick evidence that does support my belief. And then lastly, flat Earth. Rocket Man finally blasts off a homemade rocket to prove the Earth is flat. The one time they try to actually prove their experimental claims, they run an experiment where this guy goes up into space. Well, actually, he didn't even go up into space. His rocket came crashing back down to Earth. Luckily, he survived. I don't want to see anybody get hurt, even if they are flat earther. Okay, but in his brief time that he's up there, he ended up seeing that the Earth was in fact curved, thus supporting the idea, the fact that the Earth is spherical in nature. So again, any attempt to experimentally test a claim, when they do make such an experimental test, contradicts their own arguments. Okay. So why does pseudoscience still persist? Okay, if we have all this scientific evidence, why is it that pseudoscience still persists? Why are we not, in flying cars and all that sort of good stuff? Okay, so there are a couple reasons. Humans are more often than not emotional instead of logical. They'll believe what they want to believe, regardless of the evidence in front of them, and this tends to be the case with a lot of things. And an example of that is with the anti-vaccination movement. Most of the people in the anti-vaccination movement get drawn in because they have a child who has a developmental disorder or a genetic disorder that affects them, and they start looking for reasons for why does my child have a disorder? And my heart and soul goes out to them. It's certainly not an easy thing to deal with. It's anybody in that situation is going to be looking for answers, and the first answer that comes up that makes sense to them, they're going to cling on to. And that's what happens is they find this paper, and they find these group of people who say, hey, based on this paper, there's a link between vaccines and autism, and then the parents themselves become engrossed in this movement. And again, it's unfortunate, and my heart and soul goes out to them. But that's not how science works. We can't just say because a child develops autism around the same time they get vaccines that there's a link between the two. If that were the case, everybody would have developmental disorders after getting vaccines, or at least the vast majority of people, which is what we don't see. It's just a simple coincidence that children tend to get vaccines early so that they are safe and inoculated from harmful diseases and infections. And that also developmental disorders tend to start showing symptoms first around the time that adolescents turn 2 or 3 years old. I believe 2 or 3 years old. Don't quote me on that, though. I'm not a expert in that regard. Okay. So the other point is lack of scientific literacy. A person cannot understand the data that's in front of them, so they will refuse to believe it. If people aren't scientifically educated, if they don't possess a high degree of scientific literacy, even if you present them with data from experiments and all that data is accurate and supports a hypothesis, if that person doesn't have an understanding, they're going to refuse to believe it. Okay? They're going to refuse to accept it, perhaps better said. It's kind of like with language. If you don't understand a foreign language, and you can't understand it, then you're not going to believe if somebody tells you, oh, they're saying this or they're saying that, because how can you ever be sure? You're taking that on account of faith and belief. And then lastly, falsified and misrepresented data. This is the big one, okay? Data is falsified, as we'll see with the vaccine scandal, or is misreported by news media, okay? So sometimes, and this happens very, 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 very rarely, okay? There's only one big case I can think of, and that's the vaccines case, where scientists, they're human, we can be compromised. A scientist can act in an unethical manner, and falsify data for their own ends and means. Again, this very, 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 very rarely happens. But it still can occur. Okay, and other times, it's not that the data is falsified. The data can be accurate, but it can be misreported by news media. News media can come and say this is a big breakthrough, and This is going to change society, when no, it's not really going to happen. And as a result, things tend to get blown out of proportion, and people are led astray when they see these reports in the news media, and they develop misconceptions, as we'll see when we get down the line in 1.3 when we look at scientific journalism. So, falsified, misrepresented data. Okay, here's the big one. Retracted ilio-lymphoid nodular hypoplasia, nonspecific colitis, and pervasive developmental disorder in children. Ooh, let's see if I can say that 2 times fast. Ilio-lymphoid nodular hypoplasia, nonspecific colitis, and pervasive developmental disorder in children. There we go, said it the second time. This seems like a very, very trustworthy paper because it has all of these grandiose, scientifically ostentatious words, this very scientifically based lexicon. However, this study is actually false. Okay, this study was actually this was the original 1998 paper published by Dr. Andrew Wakefield, where that actually posited that there is a link between vaccines and autism. And it actually turned out that he falsified this paper. He was paid off by some lobbyists. I can't recall a specific story. He was paid off by some lobbyists, and he falsified the data in the paper. Okay, and then again with misrepresented data, we have articles like "Quantum computing breakthrough means Google could be very close to revealing revolutionary machine." That was released in 2019. Here we are in 2020, and we still haven't had any big breakthrough, okay? Quantum computing is an active area of research in physics. I have taken a course in it, and I've studied it myself. It's very, very interesting. And if we can get to the point where we can get an actual breakthrough, then it is a game changer. There's a huge potential for a huge paradigm shift. However, we are nowhere near close to a major breakthrough, and we're nowhere close to revolutionary machines. All right. Every time we make a development and make an advancement in quantum computing, it gets reported in the media as a breakthrough. Okay, so we're still quite a ways off, unfortunately, with that. So wrap up, science or pseudoscience, a man claims that when he has added salt to his crops, they grow faster. Should this be trusted? So this is what my students did at the end of the class. We'll go over this real quick. So a man claims that when he has added salt to his crops, they grow faster. Should this be trusted? No, this is an example of subjective validation. He's claiming that because it worked for his crops, they grow faster. Now, making the hypothesis is not incorrect, but going so far as to saying that this is an actual fact, that is an example of pseudoscience. He hasn't tested out his claim. He hasn't run multiple trials. He hasn't experimentally tested it multiple times. So we can't say for sure whether or not his claim is correct or not. So what we'd have to do is, we have to run experiments with controls, make sure there's no other variables that are affecting the experiment and expecting the outcome, and then run the test multiple times to see if we get consistent data. Okay, so this would be an example of pseudoscience. Second claim, a physicist admits their theory is incorrect when evidence from an experiment suggests otherwise. This would be an example of science, a scientific behavior. This is perfectly fine. Again, it's perfectly fine to be incorrect in science. That's part of the thing is when we have hypothesis, we need to test it out, okay? So a physicist isn't claiming that their theory is correct initially. They have this theory, they test it out, and they gather evidence to test out and see if their theory is correct. And then when the evidence suggests that their theory is not correct, the physicist concedes, okay, my theory is incorrect. I have to develop a new theory. And that's perfectly fine. That's how science works. It's okay to be wrong so long as we recognize that we're wrong when we are faced with scientific evidence suggesting that we need to pursue another path. Okay? And this is the lesson for 1.1, science versus pseudoscience.